How to get p-values less than 0.05 in biological research. Chapter 10. Avoid turning quantitative variables into categorical variables. You may sometimes consider turning a quantitative response variable into a categorical response variable. Here are two examples where a collaborator may suggest creating a categorical response. Example 1. A drug is intended to lower blood pressure. A collaborator suggests testing if there is a difference between drug and placebo in the proportion of subjects whose blood pressure decreases. This would change a quantitative measure, the actual measured change from baseline, into a categorical variable, improved or not improved. Example 2. A drug is intended to reduce serum cholesterol. A collaborator suggests that the response variable should be defined as categorical, either normal cholesterol less than 200 or elevated cholesterol more than 200. Let's see how using categories affects power, sample size, and p-values. In a few cases, as we'll discuss, this can be helpful. But in most cases, turning a quantitative response variable into a categorical variable will reduce power, increase required sample size, and make your p-values worse. We'll simulate some experimental data to see the p-values first, and then do power and sample size calculations. The code for creating the simulated data is at the end of the chapter. Example: creating a categorical response with two values. For our first example, suppose that the treatment is drug or placebo, and the response variable is defined to be either systolic blood pressure change from baseline as a quantitative variable or systolic blood pressure change as a categorical variable with two categories: improved, lower than baseline, or not improved, not lower than baseline. We'll use simulated data on an experiment in which subjects received either drug or placebo, and their systolic blood pressure was measured 3 months later. Here are the first 5 rows of the data. The complete data set is at the end of the chapter. Here are box plots of the data. The graphs suggest there is a large difference between the drug and placebo. Here is the t-test. The t-test indicates that there is a significant difference between drug and placebo. P equals 0.004. Now use a Fisher exact test to compare the proportion improved in each treatment arm. The Fisher test requires a table as input, so we first create the table. Run the Fisher exact test. The Fisher exact test gives P equals 0.11, indicating that there is no significant difference between drug and placebo in their effect on blood pressure. Contrast that to the t-test P equals 0.004. It is evident that changing the quantitative variable into a categorical variable has changed a significant p-value into a non-significant p-value. Let's compare the sample size required for a t-test using the measured values to the sample size required for a test using the categories. I generated the data for this example using a normal distribution with a difference, delta, between drug and placebo of 20 and a within-group standard deviation of 20. Assume the desired power is 0.8, 80%, and the default alpha of 0.05. We can calculate the required sample size using the R function power t-test as shown. Rounding up, we get a required sample size of 17 per treatment group for the t-test. To calculate sample size for the test using categories, we need the expected proportion of improved or not improved in each treatment group. We assumed an effect size of delta equals 20 for the t-test. For the next calculation, we'll assume the group means are -10 and 10 to give a difference between the means delta equals 20, which we used above for power t-test. The following code determines the proportion of the normal distribution for drug subjects that would be below 0, assuming a mean of -10 and standard deviation of 20. Running this code, we find that 0.69 or 69% of drug subjects will have values below 0, that is, improved from baseline. Running this code, we find that 0.31 or 31% of placebo subjects will have values below 0, that is, improved from baseline. We can calculate sample size and power for a test for a difference of proportions using the R function power prop test. The two proportions, as calculated above, are P1 equals 0.69, P2 equals 0.31 for drug and placebo, respectively. Again, the target power is 0.8. Rounding up, we get a required sample size of 26 per treatment group for the test for difference in proportions. Which do you prefer? A required sample size of 26 per group using the categorical variable, or a required sample size of 17 per group using the quantitative variable? If you must create a categorical variable, create more than 2 categories. If for some reason you have to change a quantitative variable into a categorical variable, you can get more power, smaller sample size, and smaller p-values if you create more than 2 categories for the categorical variable. For this example, suppose that the treatment is either drug or placebo. The response variable is one of the following. 1. Serum cholesterol as a quantitative variable, or 2. Serum cholesterol as a categorical variable with 2 categories, less than 200 versus 200 or higher, or 3. Serum cholesterol as a categorical variable with 3 categories, less than 200, 200 to 240, and 240 or higher. Here are the first 10 rows of the dataset, cholesterol data. Our code to generate the complete dataset is at the end of the chapter. The column, cholesterol LT200, shows serum cholesterol as a categorical variable with 2 categories, less than 200 versus 200 or higher. The column cholesterol category shows serum cholesterol as a categorical variable with 3 categories, less than 200, 200 to 240, and 240 or higher. Create a box plot of measured cholesterol versus treatment. Here is the t-test for cholesterol versus treatment. The p-value of 0.0038 indicates that mean cholesterol differs between drug and placebo. In the cholesterol data, the column cholesterol LT200 is a categorical variable with 2 categories, less than 200 versus 200 or higher. We can use a Fisher exact test to test if there is a difference between drug and placebo using cholesterol LT200 as the response variable. We need to create a table to input to the Fisher exact test. In the table, we see that serum cholesterol is less than 200 in 54 of the drug subjects and in 44 of the placebo subjects. The drug appears to be effective. Here is the Fisher exact test using this table. The Fisher exact test gives p equals 0.2, indicating that there is no difference between drug and placebo in the proportion of subjects with serum cholesterol less than 200. Contrast this result to the t-test, which gave p equals 0.0038, indicating a significant difference between drug and placebo. We can get a better p-value if we define serum cholesterol as a categorical variable with 3 categories, less than 200, 200 to 240, and 240 or higher, and then use a CMH test that recognizes the ordering. In the cholesterol data, the variable cholesterol category has the 3 categories. Because we have an ordered categorical variable, we will use the Cochran-Mantel-Hensel CMH test, implemented in the CMH test function from the VCD extra library. For more details on this function, see the chapter on the CMH test for ordered variables. To run the CMH test in R, install the VCD Extra package and load the library. The CMH test requires a table as input. We can create the two-way table from the raw data using the table function. We pass this table to the CMH test function. For this analysis, the relevant results are in the row labeled Armians in the output. The row labeled Armians shows the result for testing that the row mean scores differ for drug versus placebo. The CMH test gives p equals 0.019, indicating that drug and placebo differ significantly in serum cholesterol. The row labeled core is used for tables where both rows and columns are ordered. The row labeled C means would apply to tables in which the rows are ordered but columns are not ordered. The row labeled general is similar to the chi-squared and Fisher tests. Let's compare the results from the three different ways of analyzing this data set. The Fisher exact p-value using two categories is not significant. P equals 0.2. In contrast, the p-value for three categories using the CMH test for ordered categories is significant. P equals 0.0191, and much closer to the p-value using the t-test with quantitative values. P equals 0.0038. When you create the categories, it is desirable that there be a plausible reason for selection of the thresholds that define the categories, and that there be a good number of observations in each level of the categorical variable. Logistic regression and ordinal logistic regression for categorical response variables. An alternative to the CMH test for categorical variables is logistic regression. If the response variable has only two categories, then you can use the standard version of logistic regression. If the response variable has three or more ordered categories, you can use ordinal logistic regression. Ordinal logistic regression is available in the R package POLR. The UCLA Statistics website on ordinal logistic regression has a good introductory tutorial on POLR. The UCLA Statistics tutorial website is a great resource that I highly recommend. There are many very helpful and easy to understand tutorials on analyses using R and other statistical software. When can it be helpful to use categories instead of quantitative measures? I've occasionally encountered situations in which it was helpful to turn a quantitative variable into a categorical variable. Here are some examples. Example 1. Extremely inaccurate quantitative measurements. If the supposed quantitative measurements of a variable are extremely inaccurate, the quantitative information may be less informative than categories. In a data set that I examined many years ago, the supposed quantitative measure was the expression level of a gene, based on fragments of mRNA recovered from some quite old paraffin-embedded tumor blocks. If you have tried this yourself, you likely know that the mRNA is highly fragmented, and the resulting gene fragments can be difficult to assemble into a complete sequence. At the time I was doing this, the Human Genome Project had not been completed, so we had no reference sequence for many genes. I examined correlations among genes known to be in the same regulatory pathways, or known to have related biological function, but found none of the results made any sense. Eventually, I replaced the quantitative measure with a categorical indicator that a particular gene was either found expressed or not found in a particular tissue specimen. Instead of correlation, I used a Fisher exact test to examine the co-occurrence of genes. The analyses using the categorical indicator, variable, and Fisher exact test were able to reproduce known associations and contributed to finding likely functions of many genes. So, in this case, turning a quantitative variable into a categorical variable proved useful. Example 2. Biologically meaningful categories. In some cases, an easily obtained measured variable such as age may be a proxy for a biologically meaningful category, such as premenopausal versus postmenopausal status. For a model of cancer versus gene expression, we might consider adding age as a covariate, as a proxy for menopausal status. If the true menopausal status is the biologically meaningful covariate, but it is not known, then an analysis may yield better results if we create a categorical variable, such as, for example, age less than 50 versus age 50 or greater as a proxy. We might alternatively consider three ordered categories for age, such as less than 50, 50 to 60, and over 60, corresponding to pre, peri, and postmenopausal. Example 3. Nonlinear response. In some cases, the relationship between two quantitative variables may not be a straight line. Testing using correlation or regression may not work well. In this case, it can be useful to split one or both variables into meaningful categories and use either ANOVA or CMH to test for association. Here are the R data sets. CBP data. Use setSeed to make the randomly generated data from the R norm function reproducible. Rows 1 to 10. Rows 11 to 20. Rows 21 to 30. Rows 31 to 40. Cholesterol data set. Cholesterol data set continued. The last cholesterol data set. Visit mwalkerstatistics.com to download R code for all examples and get the free companion book in PDF format, or order a copy from Amazon